Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a large-scale messenger system, the kind of real-time chat infrastructure that powers WhatsApp, Facebook Messenger, Telegram, and WeChat at billions of messages per day. We'll cover WebSocket connections, message delivery guarantees, online and offline presence, typing indicators, read receipts, media storage, and end-to-end encryption using the Signal protocol. Whether you're preparing for a senior engineering interview or building real-time communication infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a large-scale messenger system, the kind of real-time chat infrastructure that powers WhatsApp, Facebook Messenger, Telegram, and WeChat at billions of messages per day. If you have ever wondered how your message goes from your phone to your friend's screen in milliseconds, how typing indicators and read receipts work under the hood, how online and offline presence is tracked at scale, how media files are stored and delivered efficiently, or how end-to-end encryption keeps conversations private, this video is for you. We'll walk through the functional requirements, non-functional requirements, high-level architecture, end-to-end user journey, core models, low-level design, and the key trade-offs that come up in a senior system design interview. Whether you're preparing for a FANG interview or building real-time communication infrastructure, let's get into it. Here is the core problem. Billions of people rely on messengers like WhatsApp, Telegram, and WeChat to communicate instantly, at any time, from anywhere in the world. The challenge is deceptively simple on the surface. Send a text message from one device to another. But the engineering complexity is enormous at scale. You need to deliver messages reliably even when the recipient is offline, store conversation history durably, track online and offline presence for hundreds of millions of users simultaneously, handle typing indicators and read receipts with minimal latency, support large media files including images, videos, voice notes, and documents, and do all of this with end-to-end encryption, so that not even the platform operator can read the contents. The system must handle billions of active sessions, survive data center failures, scale horizontally across regions, and still feel instant to every user on the planet. That is the real problem we are solving today. Let's walk through the functional requirements. First, the system must support one-to-one messaging with reliable delivery, meaning a message sent by Alice must reach Bob, even if Bob is currently offline, and must never be lost. Second, it must support group messaging with delivery to all members, with appropriate fan-out at scale. Third, it must track and broadcast online and offline presence, so users can see when their contacts were last active. Fourth, it must support typing indicators so a user knows when the other person is composing a reply. Fifth, it must support read receipts with delivery confirmation, sent confirmation, and read confirmation, the classic single tick, double tick, and blue tick pattern from WhatsApp. Sixth, it must support rich media, images, videos, voice notes, documents, and stickers, with efficient upload, storage, and download. Seventh, it must support end-to-end encryption so message contents are private even from the platform. And eighth, it must support message search, notifications, and multi-device sync. Now the non-functional requirements. The system must be highly available. Messaging infrastructure is mission-critical, and even a brief outage affects millions of users. Latency must be extremely low. Message delivery to an online recipient should feel near instantaneous, under 100 milliseconds end-to-end in the same region. The system must scale to billions of users and tens of billions of messages per day, with horizontal scalability at every layer. Durability is critical. Messages must never be silently lost. The system must be consistent enough that messages appear in the correct order in conversations. Presence and typing indicators can tolerate slightly relaxed consistency, but message delivery cannot. The system must be secure by default, with end-to-end encryption, transport layer security, and strong authentication. And it must handle the thundering herd problem, where a single popular group or a major event triggers massive concurrent activity. Here is the high-level system architecture. Clients, mobile and desktop apps, Connect to edge WebSocket servers via persistent long-lived connections. These WebSocket servers maintain the connection state and route messages. An API gateway handles REST requests for non-real-time operations like account management and media uploads. A message service receives messages from the WebSocket servers and coordinates delivery. For online recipients, it pushes messages directly via the WebSocket connection. For offline recipients, it queues messages in an offline message store and sends push notifications via APNs and FCM. A presence service tracks which users are online, their last seen timestamps, and routes presence events. A media service handles upload and download of large files through object storage like Amazon S3. A group service manages group membership and handles fanout for group messages. All services communicate asynchronously through a message queue like Kafka, and data is stored in a combination of Cassandra for messages and Redis for presence and session state. The key metrics to memorize cold. Message delivery latency is the time from a user hitting send to the recipient receiving the message. Target under 100 milliseconds for online users in the same region. Message delivery rate measures the fraction of messages successfully delivered within the SLA. Presence update latency is the time it takes for an online or offline status change to propagate to relevant contacts. Target under 5 seconds. Read receipt latency is the time from the recipient opening a message to the sender seeing the read indicator. Media upload and download throughput measures the speed of file transfers, which affects user experience significantly. Daily active user connection count tells you how many concurrent WebSocket sessions the infrastructure must maintain. And message storage costs per user per month drives infrastructure budget decisions, since messages and media accumulate indefinitely unless pruned. Let's trace the end-to-end user journey. Alice opens WhatsApp on her iPhone. Her client establishes a persistent WebSocket connection to the nearest edge server. She opens a chat with Bob and starts typing. The client sends a typing started event to the presence service, which fans it out to Bob's connection. Bob sees the 3-dot typing indicator appear. Alice hits send. Her client encrypts the message using Bob's public key via the Signal protocol, then sends the encrypted payload to the message service. The message service acknowledges receipt and assigns a server-side timestamp and message ID. Since Bob is online, the message is pushed directly to his WebSocket connection. Bob's client decrypts it locally and displays it. The client sends a delivered receipt, then a read receipt when Bob opens the message. Alice sees the double tick turn blue. If Bob had been offline, the message would have been stored in the offline queue, and Bob's device would have received a push notification on reconnect. The core models and algorithms. The message data model stores message ID, sender ID, recipient ID or group ID, timestamp, encrypted payload, message type, and delivery status. Messages are stored in Cassandra, partitioned by conversation ID, and sorted by timestamp for efficient range queries. The fanout model for group messages must balance write fanout, writing 1 copy per member at send time, against read fanout, storing 1 copy and expanding at read time. WhatsApp uses write fanout for small groups and a hybrid approach for large ones. Presence is modeled as a heartbeat. Clients send a heartbeat every 30 seconds, and the presence service updates a Redis key with the last seen timestamp. If no heartbeat is received within 60 seconds, the user is marked offline. The Signal protocol provides end-to-end encryption using a combination of the X3DH key agreement and the double ratchet algorithm, which provides perfect forward secrecy. Offline message queuing uses a durable store keyed by recipient user ID, with TTL-based expiry for ephemeral messages. Now the low-level design deep dive. The WebSocket server maintains a connection registry mapping user ID to connection handle and server ID, stored in Redis so any service can look up where a user is connected. When a message arrives, the message service checks the registry. If the user is online, it sends to the specific WebSocket server via an internal pub sub-channel. If offline, it writes to the offline message store in Cassandra with the pending delivery status. The media pipeline uses a two-phase approach. The client gets a pre-signed upload URL directly to S3, uploads the file, then sends only the metadata and URL in the message payload. This keeps large files off the message service entirely. For message ordering within a conversation, the system uses a logical clock, a monotonically increasing sequence number per conversation, stored in a distributed counter in Redis with compare and swap semantics. The notification service integrates with APNs for iOS and FCM, for Android to wake offline devices. Multi-device sync is handled by maintaining per-device delivery state and syncing across devices using a device inbox pattern. Key takeaways for your interview. First, persistent WebSocket connections are the foundation of real-time messaging. Understand why HTTP polling does not scale and why long polling is a stepping stone to WebSockets. Second, message delivery guarantees require at least once delivery with deduplication on the client side, using message IDs to discard duplicates. Third, presence at scale is an approximation. Heartbeats and TTLs provide eventually consistent presence, rather than perfectly accurate real-time state. Fourth, end-to-end encryption with the Signal protocol gives you perfect forward secrecy and deniability, but it means the platform cannot read messages or recover them if the device is lost. Know this trade-off. Fifth, fan-out for group messages is a classic write amplification problem. Small groups fan out at write time, large groups use a hybrid or read time expansion. If you can walk through these 5 points with the full architecture, you will signal strong senior-level design thinking. That's it for Design a Messenger. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on Design a Messenger. We covered the full picture, from persistent WebSocket connections and real-time message routing, through presence heartbeats, fan-out strategies for group chat, offline queuing, push notifications, and end-to-end encryption with the Signal protocol. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.